Hello everyone and welcome to a new session of CMSL presentations. My name is Miguel Recio-Poo and I will be your host today talking about one of my latest PhD projects, which title is Tuning Electronic Levels in Photoactive Hydroxylated Titania Nanosystems, combining the ligand dipole effect and quantum confinement. So first of all, it is important to remark that Titania is relevant due to its use as catalyst for water splitting. Water splitting is the breaking down of water into its main constituents and is a good way of generating hydrogen, a clean energy source. However, this reaction is not spontaneous at ambient condition, it goes against thermodynamics, so it needs an external energy. For example, in photoelectrochemical cells, Titania is used as a catalyst, absorbing light and generating electron and holes that facilitate this reaction, generating hydrogen and oxygen. For this reason, the bondage positions of Titania, and especially its relative position with respect to hydrogen and oxygen redox potentials, are of key importance. In this way, in this project, we have analyzed the effect of hydroxylation and quantum confinement on such band edges. Those are the different Titania models we have used here: 3 faceted bipyramidal nanoparticles, 1 roughly spherical annealed nanoparticle, and also a 101 anatase surface model. With Ames computational code, we have done a PV optimization of the structures, and also we have implemented a hybrid-inspired PVX correction for getting a more accurate value of the gaps. So yeah, we have analyzed the band gap of all the systems, the evolution of band edges, and lastly, the relevance of all of this to water splitting. So first, I show here the evolution of the electronic energy gaps for the different systems, and you can see that at first, when the degree of hydroxylation is 0, the 35 nanoparticle, the smallest one, exhibits the largest electronic energy gap, due to the effect of quantum confinement that is maintained with hydroxylation throughout all the degrees of hydroxylation. Moreover, hydroxylation also induces an increase in the energy gap, which is due to the healing of undercoordinated atoms and defects. And for the 35 nanoparticle, as it is the structure with a larger proportion of undercoordinated sites, it undergoes the larger increase, the larger variation in the electronic energy gap. Okay, so this is what concerns to gap, but someone may ask what is happening exactly to band edges. For this reason, I show directly here the evolution of both HOMO and LUMO frontier energy levels defining the gap, and you can see that there's an initial steady increase with respect of hydroxylation, and then when some degree of hydroxylation is reached, like 50%, there's like an stabilization, like if the rate of increase slows down. This effect on the band edges on all the levels has been reported several times in the literature by other research and is normally referred to as LIDE, ligand-induced dipole effect. So hydroxylation causes this upshift in orbital energies due to this ligand-induced dipole effect that is coming from the cumulative electrostatic field of all surrounding dipolar OH groups. So as more OHs we have that come from hydroxylating the system, we will have a larger effect. But as we can see here, it is not strictly linear all the time, but it has two different linear regimes. So we need a model that captures both regimes. So we propose this refined model in which the total dipole is calculated with the positive charge on the H atoms in every OH ligand, and also to project the dipole towards the center of the nanoparticle, we also take into account the distance between OH in each ligand and also the cosinus between titanium, oxygen, and hydrogen. So the novelty here, and this is why we call it refined model, is that we have realized that depending on the degree of hydroxylation, the alpha angle and the positive charge on the H atom go down and become closer to 0. And this is due to the fact that there has been forming OH-OH hydrogen bonds. There's like an H-bonded network that promotes this bending on the alpha angle and also the delocalization of the positive charge, making both quantities decrease for larger and larger degrees of hydroxylation. So with this expression, we can then calculate the shifting on the energy levels. For example, like here, I show the HOMO and LUMO variation for the smallest and largest nanoparticle, and we see that there's a strong correlation, there's a very good agreement between the energy shifting and the total dipole obtained. For calculating the energy shifting then, we have used the expression shown in the left-hand side of the slide, in which the energy of the bare case is taken into account, plus this other term that considers A, which is a fitting constant, but more importantly, the total dipole dependent on the number of ligands, as you showed in the previous slide, and also the size of the nanoparticle with this R square term. So lastly, what is the relevance of all this to water splitting? To illustrate this, I show here this nice plot in which, taking into account the hydroxylation of the system and the nanoparticle size, which goes in the reverse way than the quantum confinement, you can tune a property for the desired application. For example, here I show the LUMO energy and how, when it is with some degree of hydroxylation, some nanoparticle size for this kind of systems, you can tune it to be slightly above, on top of the hydrogen evolution reaction, which is the desired situation that you want for efficient generation of hydrogen. So yeah, combining the ligand-induced dipole effect and quantum confinement allows one to tune the system energy levels, in this case for generating hydrogen. So yeah, those are the conclusions. What have we learned today? First of all, that the quantum confinement effect and increasing the degree of hydroxylation raise the gap in all Titania systems. Also, we have proposed this refined model taking into account the stabilization, which models the ligand-induced dipole effect that promotes the upshift on band edges. This upshift is electrostatic in nature. And lastly, as I showed in the previous slide, combining the effect of ligand-induced dipole effect and quantum confinement allows one to tune the energy levels with consideration of practical constraints, which in our case was generation of hydrogen, which is the main goal of sun-driven water splitting. So yeah, lastly I want to thank my supervisors, my tutor, also the different agencies for their help for funding my project, and of course you for your kind attention. See you soon, bye bye, thanks.